So it was found at some point that whenever you pass an electric current through a conductor, it actually creates a magnetic field around it. So what we'd have is we'd have the direction of the current like this, and we would see a magnetic field being created around that. And if you remember, the way we relate the direction of the current to the magnetic field is using this right-hand grip rule. So if we've got the current going in the direction that our thumb is pointing, what we get is this circular magnetic field going around like this. So we can maybe represent it like this. So that's it coming from behind. And so we can use an arrow to show that as well. What we can also do when we show this in diagrams is show the field lines getting further apart as we go further from the wire. And that's showing that the field is getting weaker when we go further away. Now, why is this important? Well, because it creates a magnetic field and we can get magnetic objects such as compasses. What we can then do is we see that we can use this current in a wire to create a force. And that is the absolute basis of all electric motors, which you'll find in so many things. For your phone, laptops, electric cars, obviously. But this is the fundamental principle. And what we can do is we could use a lot of little plotting compasses and put them around this, and they would show the direction of that because they would all be pointing along this way. And they would also be shown this, they would be showing this radial or this circular type pattern. So sometimes you will see this, they will ask you, okay, so here is a wire going into the page. What direction does the current go? Sorry, the current is going into the page. What direction is the magnetic field? And so you would get your right hand, point in because the current's going into the page, and then you would use those fingers to represent the direction of the magnetic field. Well, and you'd probably do it better than that. And it's at increasing distance, which shows that the field is getting weaker. So this distance is shorter than this, or it's shorter than this one. Okay? Now, the next thing we want to think about is the forces that are actually created in those. So what we could have is we imagine here's a north pole to some magnet. Okay, we'll just call it N. And we're going to have the south pole to this magnet. Okay, so they're placed opposite each other. And what we can do is we can, because these are parallel facing each other, we can show the field lines maybe like this, going from north to south. And then if we put a wire into this, so we take that electrical wire and put it into this magnetic field, and then we switch the current on, well, what do we see? Well, this is where, again, we have to remember another of these rules, and this time we use our left hand. And we've got three different things the left hand tells us about. Okay, so the first finger is the field. The second, the cursing finger, is for the current. So we can line two of these up. So there's the field. Okay, the current's going the other way, so a little bit of contortion here. But there's our magnetic field. And we can see that our current is going the opposite direction to this, which means the force on this wire is going to be into the page. Now, the wire and the magnets are magnetic objects. The magnets will also feel an equal and opposite force. So as the wire goes into the page, well, actually there's a force out from the page on the magnets, but of course the wire moves a whole lot more because it's got a much smaller mass. Okay, but you have to remember that it is equal and opposite. So there's the absolute fundamentals of electromagnetism. I'm going to check the syllabus to see if there's anything else I want to talk about in this. Oh yeah, so there's another thing as well. What we can do to increase the strength of this magnetic field that we're creating is we could wrap the wire up. We get more turns, and what we get is the fields kind of, they add. Because we wrap them up in like a circular sort of pattern, they don't add in a simple sort of way. But what we get is an increased strength. So this, if we imagine my crude drawing as being just wire coiled up in a long series of, well, not really circles, but coils. This is what's known as a solenoid. Somebody's asking me a question here. We've got a solenoid, and we'll say the current is going this way. Okay, so I and I. All right. So again, what we can use is this right-hand grip rule. And what that tells us is that, no, actually you don't need to know that, which is lucky because I can't remember it very well. But what we get is inside the solenoid, the field is uniform. Outside it, we get a field just like a normal magnet. So what we get is a field like this. with increasing distance to showing decreasing strength. But of course, at the poles, we get these strongest areas. Okay, so you wrap those up and make a solenoid. Now that's very useful because because we wrapped it up, we get a much stronger magnetic field. What else did I want to talk about? Oh yeah, so the field lines go like this here. I just Google it. So it goes in this way. So the field lines are going like that. So that means whenever you line up magnets around it, you'll see that particular field being given. Sorry, not magnets, compasses. Okay, and yeah, so we'll leave it at that. I'll make a separate video for motor effective things.